ran back to the US when it became clear that international flights were shutting down. So in fact, the sunset scene is about the right timing here in Philadelphia. It is, and I am sorry to have not spent more time at ANU. That's where I did my undergrad degree, and it's always lovely to be back in Canberra. So it's great to see you all, at least remotely. So this work is joint with a whole lot of people, since I'm at the sort of stage in my career where a lot of my work is done with students. A large part of this, I wonder if I can highlight. I can't. I'm still learning to do formal Zoom seminars, is with Lucas Mensch, a former student now at the University of Pittsburgh, and my grad student, Tim Coleman. You'll see some of this stuff, as well as former students, Ichan Zhou and Sarah Tan, and some current students, Jungsu Zhou and Indra Gosal. It's also benefited enormously from a long-standing collaboration I have with Cornell's Lab of Ornithology, in particular Dan Fink, a statistician there, Steve Killingworth, Hachachka, Frank Lesort, and David Winkler, and you will see some of the wonderful data that they've collected during the talk. I know that ornithology is a little bit surprising, but we'll get there. So for this talk, I want to talk about machine learning and translating machine learning into questions about statistical inference. And in particular, we'll talk about random forests and bagged trees and their connections to formal statistical structures in view statistics, and how you can use them to do confidence intervals, to develop tests, and in particular with respect to the Ebird program that the ornithology lab has had. With some extra time, I will talk about some of Jungsu's work on improved variance estimates and variations on random forests, and Ichan and Indra's work on boosting, again, if I get time. Tao, I presume you have some way of telling me I'm going over if needed. As Tao already indicated, I do some work in other areas. I spent about a dozen years and wrote a book on nonlinear dynamics and statistical inference, functional data analysis, and some robust statistics, and I'm happy to talk to anybody who's interested about any of that work as well. Okay, so just to get some stuff straight, and I used to call this talk a tale of two theses, being the PhD thesis that I wrote 100 years ago, and then Lucas, who came and wrote the PhD thesis that I should have. That's no longer quite fair because I've progressively taken my own work out of it. But just from a perspective of what do I mean by some of these terms, because some of them have gotten a bit fuzzy. So for me, or at least the purposes of this talk, machine learning really means high-dimensional non-parametric prediction. You know, the topic as it's taught tends to cover things like clustering and exploratory data analysis, or certain types of exploratory data analysis, and that's well and good, but here's what I'm going to focus on. It's been enormously successful over the past 30 years or so, and I don't really need to tell you a whole lot about that in terms of, you know, all of the wonderful tasks it does in machine translation and recommender systems and image processing and a whole bunch of other stuff as well. But part of the success is that it has deliberately avoided modeling assumptions. It's, you know, linear regression or any of these types of models are not part of what they want to do. The philosophy has been very much, just give us the data and our machine is going to work it out. That's resulted in algebraically complex black box functions. What you get out is something that is a mathematical formula to get you from input to output, but it might be some 500 pages long. And that provides fairly little guidance as to what features are important or how they affect predictions. And it provides little by the way of statistical inference. So providing some additional indications about what this model is doing has actually really helped historically to boost the popularity of the models. But they're all based on heuristics, and we'll talk a little bit about some classical methods out of gradient boosting and random forests. But they haven't been, until recently, very carefully thought about. And again, certainly not formal inference. So a bit of notation. I am going to assume that I have a data set of n observations, xi, yi, and if I'm talking to a computer scientist, these might also be called examples or realizations. Each xi is a feature of p covariates, also features or predictors or variables. You notice that computer scientists manage to hook onto much more emotionally high valence terms than statisticians like, but there you go. And I'm going to use this data set to estimate or learn or train a prediction function f that is going to be a function of input, these p inputs, and spit out an output. So xi is going to indicate a row of a data set. If I use a .j, that means it's the jth column. And if I use negative subscripts, that means everything except that particular subscript. And okay, what I wanted to do as a PhD student was to understand what that f was. And what we then progressed to do is to say, well, we want some idea about the statistical stability of that understanding. Okay, so just to make all of that concrete, let me tell you a little bit very quickly about random forests. So random forests are an ensemble of trees, and briefly, they look like a tree glyph. So what they do is they split up your covariate space into disjoint rectangles that are made according to a tree. So this will ask, you know, is x1 less than some number? If it is, go left. If it's not, go right. You'll be asked about x2, again, left or right, and you get down to a leaf, and you'll get down to a prediction for what you will give. So in a two-dimensional space, this has just divided the space up into rectangles with a constant prediction in each. And you can generalize that to higher dimensions fine. You get to this model via a greedy algorithm in which you, at the top node, just find the best split that you can so that the prediction, you've maximally improved your prediction on either side. Then you come down to the left, so over here, and you say, how can I split this region up to, again, maximally improve my predictive performance, however that's measured. In regression, squared error is general. You might talk about, well, the Gini index or binomial log likelihood in a classification setting. Now, this produces a nice, in fact, understandable model when the tree isn't huge, and you know, looks pretty good. There's in fact quite a lot that's nice about tree methods, but they don't actually predict very well. Basically, they tend to overfit the data very quickly because I split my data up divide my data up very quickly, roughly in half each time I split. But I also tend to have like these big, wide regions. So I managed to combine both high bias with high variance. It's a neat trick. And beyond that, this greedy splitting process is very difficult to analyze mathematically and to get a handle on. And you tend to get only very conservative and loose results as a consequence. By the way, I think it is possible for you to like put up a hand or just to interrupt me. I'm very happy to take questions as we go through. What has worked much, much better are ensembles of trees. These come in a variety of methods. The earliest of these was bagging, which Leo Breiman introduced in '96. And he basically said, look, one single tree doesn't work very well because it's very sensitive to the way the structure of the tree changes as you change your data set. But what you can do is to put up many trees and average them. So in particular, what he suggested doing was to take a bootstrap sample of data, of your data set, build a tree using that bootstrap sample, and do this B. B was usually 500 or 1,000 times. And then when it comes to making a prediction at, say, a point X star, and the reason I've written this process as a function of my bootstrap sample that's defined by a prediction point will become apparent later. But when it comes time to make a prediction, you make a prediction from every tree, and you average the predictions. If you need a class label predicted or something like that, you can then threshold that as though it's a probability. And this did a whole lot better at stabilizing what the trees look like. Random forests Brown then came out with random forests in about 2001, which were very similar to the bagging idea, except that he added some extra randomization during the tree building process. Not just take a bootstrap sample, but every time you come to take a split, rather than looking at all possible covariates and all possible ways you could split, I'm going to only choose a subset of the covariates to examine as potential splits. And I'm going to do that randomly at each split point. And the idea was to say, I want to decorrelate these trees so that the averaging process ought to work better. And these ideas will also come up a little bit later on. These are one of the best off-the-shelf machine learning tools out there at the moment, at least as a general process purpose method. You can certainly do a lot better with things like deep learning technologies and neural networks in highly structured specific types of tasks. But for I've got data, I don't have to think much about it, and I don't have the time, you can throw it at random forest and it will fairly reliably do pretty well. The trees are not really sensitive to scaling your data or to transforms of your data. They have relatively few tuning parameters, and random forests are fairly insensitive to those tuning parameters. They work really quickly. So you can kind of throw data at a random forest. They also have some funky ways of dealing with missing values and get answers and say, this is going to be pretty good without a whole lot of human effort and intervention. And for that reason, they've been super popular. So if you go to the predictive competitions website, Kaggle, they have a baseline. Their baseline is a random forest because, again, you can just chuck the data at it and not have to think very hard. And that's going to be important also for the lab of ornithology in a minute. So what do you want to do with these? Well, you might ask things like which covariates are important. One of the ways that you measure this is what's called permutation importance, in which you say, well, I'm interested in measuring the importance of x.1, so the first column in my data, in my covariate space. What I'm going to do is I'm going to permute that column, meaning I'm going to the relationship of that column with all the other covariates and with y, and I'm going to measure how much changing x1 to its permuted value affects the prediction I make. I can also look at how much it degrades my performance, my predictive ability as well. You can also look at how much each individual split difference each individual split makes. I'm not going to go into that at the moment. You say, okay, x1 matters. How does it matter? Well, you might ask, how does f change as you change x1? And you could think about saying, well, I'm going to make a prediction, and then I'm just going to replace the value of x1 with a particular, with a okay, for each prediction, I get a whole function of whatever the range of values happens to be. And then if you also, then, you know, okay, so I've got a whole bunch of these lines. What Friedman said was just average them all. And so you get a single line that's the average effect of the value of x1. Now, I'm going to stop and do a little brief aside about why this is an incredibly bad idea. It's not incredibly bad, but why this is a bad idea. You can relate all of these to something called the functional ANOVA. And I wrote a thesis on looking at them. But what they do is they break up relationships between x1 and everything else. And so just to illustrate what happened, why this is a problem, here I've produced a pseudo data set in red points in 2 dimensions with x1 and x2. And in the blue points are all the places in which predictions are made that go into this measure of variable importance, or would also go into calculating a partial dependence plot. And the point here is that there is an awful lot of weight that goes into this region where I have no data, but I'm nonetheless making predictions. And that can actually very seriously distort what you see. Is that real? Well, here's a brief experiment in which what I did was to create a actually 10-dimensional covariate space. X1 and X2 are correlated. X3 through X10 are not. They're all marginally uniform, and I correlated X1 and X2 with a Gaussian calculus. So if you can make out the little points on the right-hand plot here, those are data points. And then we measured the variable importance by commuting variables of a linear model or a neural network or a random forest, and asked what the combined rank of the importance was for x1 and x2. Now, these guys had equal, the response was a linear combination of all the covariates with, I think in this case, equal coefficients for each. And what happens as I increase the correlation between x1 and x2 is in all of these other models, reliably ranked to be more important than all of the others. I can make them more important without going to extremes, even if x1 and x2 have lower coefficients than all of the others as well. And part of the reason for this is that what I've got as all of this horrible hatching is these are the splits of the first 6 decision trees in a random forest. And you can see what's happening is the prediction that I make out at these corners where I have no data basically comes from one end or other of the prediction. And so it's like I am giving x1 and x2 both the marginal regression on their coefficients. That's not an exact statement, but as a sort of intuitive explanation. And this effect is to say that correlated predictors are ranked as more important, which is in fact pretty much exactly the opposite of what a statistician would expect. But continuing back onto something of more interest. I see a query that I might be, my audio might be an issue. Let me slow down just a minute and check. Okay. So, yeah, can I stop my video, which is not necessarily great for everybody, but that might hopefully make things better. So let me tell you a little bit about the Ebird project at the Lab of Ornithology. Ornithologists have been doing citizen science for basically longer than anybody else. There are bird counting programs with publicly collected data that go back into the 1890s. In this case, in the late 90s, Cornell started up an internet-based service called Ebird, and in which bird watchers record observations. They pay the Lab of Ornithology for the privilege of giving them data, which is kind of a neat trick. There's a subscription model. But you go out bird watching, you come back, you log on to the Lab of O, and you record, I was at the following place following time with a certain number of people for a certain amount of time. And these are the numbers of, I saw each of the numbers of the following species. We give them a list of species that they are likely to see, so that we can count the species they do not list as being zeros as well. So we do have both presence and absence. With a GPS location or time coordinate, we can get a bunch of GIS data about the local land cover, land use, water availability. There's some thousands of potential summaries that you can get out of this, as well as weather covariates, and we're only just starting to put some of that in. This is now, I think, a year old since I updated this slide, and we were north of 600 million records in that data set, and again, some thousands of covariates, although we normally restrict what we actually look at to about tens. What do they want to do with this? Well, they want some maps of where the birds are. When you look at a standard bird book, these are just some expert has kind of drawn something in by hand. We want to generate some hypotheses about bird ecology. We want evidence for changing bird behaviors, especially under climate change, and they're starting to try and actually forecast bird migration, although that's a bit out of the scope of this particular talk. To do this, they have something that looks very much like a random forest. They localize, they build trees on specific patches of data that are defined by spatial and temporal extent, just to prevent some bleeding over of signal, but otherwise it looks very much like a random forest, and this is stuff that Dan Fink developed about a decade ago. So what I need to do now is show you, so here's things that you get. Partial effects, so these are the partial dependence plots that we would pick out of some of these models as the most important effects that we observe, or the largest effects we observe of individual factors. Year and elevation seem to be big ones. It's not surprising. We found some interesting interactions about grassland species that move into forest habitat when you put roads through. If you think about it, it's not terribly surprising, but it wasn't something that we had sort of previously hypothesized about. And in a big collaboration with the the Audubon Society, they produced a whole lot of maps about where birds were. So I need to stop this and reshare a different application here. Oh, not the right one. Just a minute. Okay, share screen. Here we go. I hope that you can now, so just, is a movie playing for you? Because I can't actually tell if this is being shared. Somebody?
I didn't see a movie.
Okay, let me make sure that I have, thank you. I need to click share, that would help. There you go. So this should be a little more obvious, evident for you. So this is a map of this bird, indigo bunting, that overwinters around the Caribbean, but migrates up to the northern latitudes of Alaska and Canada to breed. And basically, I'm playing one screen a day, and you can see the intensity. And so this is technically the probability of observing an indigo bunting if you go out bird watching at 7 a.m. for an hour each day. You can see the migration pathways come up as a fairly concerted effort through most of the US, although Florida lights up into their summer breeding grounds, and they come back down. You can see the Central Valley of California lighting up, the Mississippi River Valley as well, and into their breeding grounds as well. And if you told me that you could do something that detailed based on random forests, I would have frankly laughed, but it's amazing what millions of observations will do for you. Okay, so these are the sorts of products that we're producing. Let me get back to my slideshow again. And, oh, how did that happen? Right, that's where I was. Okay, but we might be asked, and so what we get is, you know, predictions for individual cases, some measures of structure, and people have been interested in explanations for particular predictions as well. That is mostly in terms of very locally what affects those predictions a lot, or which covariates matter. But you might be asked, well, you know, we're statisticians, you're inclined to ask, how much do I trust these results? So what I would like is some notion of a confidence interval for outputs for the predictions that I make for some of the summaries. Some of those suggest hypotheses. I'd like to test them. And I'd like to make this computationally feasible. The parenthetical comment here is basically because those movies were made using the National Science Foundation supercomputer at the time. There were some 700 species that the Lab of Ornithology agreed to produce those sorts of maps for. And they loaded it up on the Terra grid and promptly crashed it. And there were some very nasty emails that came around. So running at once on that scale of data is challenging. Bootstrapping that is just not going to be feasible. So we're not going to bootstrap our bagged trees. But we'd like some idea about resolution. Now, theoretically, the greediness of the structure, of tree structure, is really going to be hard to work with on an individual tree basis. But we might be able to rely on using the structure of the ensemble. So that's not quite as easy as you like. This is an average, right? And there's some bootstrapping going on. So, you know, you think, hey, bootstrapping is good for uncertainty quantification. But I want inference about the average of bootstrapped estimates. Not a bootstrap will give me a notion about the average, the uncertainty in one estimate. Now you could say, hey, it's an average, we can apply a standard CLT. The problem is that those trees are highly correlated, and on bootstrap samples, the correlation doesn't go away as you get more and more data, or at least the overlap between any two trees is expected to be about 63%. So I can't very readily just sort of use standard results. Now, one thing you can do, though, is to say, well, if the correlation between trees is a problem, maybe what I should do is take subsamples instead of bootstrap samples. So I'm going to make that single change, and I'm now going to say, okay, I've got an estimate that is an average of B sub n trees, each of which is built on a bootstrap on a subsample of size kn. Okay, now we're starting to get somewhere, and when you look at it, you say, okay, here is my expression for my model, or for a prediction. So for a prediction at x star, I'm going to write this as bn times, take a subsample, build a tree, predict from the tree, average those. Now, obviously, I'm going to not do build a new random forest every time I make a prediction. But this is useful to think about because it makes it clear that this is very closely related to a classical statistical concept of a U-statistic, which is basically saying if I have some function h of data that calculates something I'm interested in, and it needs k data points, but I have n, what should I do? Well, I'm going to take every subset of size k, plug it into h, and average them. And this comes up in terms particularly of rank statistics classically, but you can express moments in these terms as well. Now, the nice thing about them is that under actually pretty mild conditions, U statistics have a nice central limit theorem. So that so long as my individual kernel has a variance, then there's a central limit theorem in which my U statistic is centered around whatever it's trying to estimate, with a variance that whose expression I will get to in a little bit. Okay, so I need to do a little bit more work here to get this into random forests, and there's a few things that go on. Theoretically, the stuff that you mostly read in papers is developed for a kernel of fixed size, i.e. K is fixed. It's normally things like comparisons between, is this data point larger than that data point in classical terms. Now, that's obviously not going to be what we want to do. If we get more data, we'll want to build deeper trees. That means we need to take larger subsamples. So we need to have our K grow as N does, and this creates what's called infinite order U statistics. Computationally, I'm not going to take all N choose K subsamples. That would be just stupid. And if it's just completely infeasible. So what I'm going to do is to choose subsamples at random. That produces a incomplete U statistic. And algorithmically, we have additional randomization that goes on when we build a tree, when in the case of random forests, you choose subsets of covariates to look at each time you create a split. So I have non-deterministic U statistics. This is something that we've started calling generalized U statistics. I started with random kernel, but generalized seems to be funkier. But these are epicycles on the great big crank that you're turning, and so you can go through some work with a theorem that Lucas and I proved in a 2006 paper, but he and his students have come back and refined it considerably last year, where you say, okay, if we have this form of an estimator, I'm going to include omega I as a random, extra random number that I put into each tree. So if I have this ensemble of B learners based on this tree building process T, although there's nothing so far that we've said in any way that actually assumes a tree. It's just something that takes a subsample and produces a prediction. Then I'm going to define two variance components, which I'll talk about in another slide. And so long as those variance components don't get too out of whack, and this is fairly reasonable. It's written a little bit funkily, but basically if your subsample size gets small relative to N, although not necessarily very quickly, and one variance component is not too much larger than the other, then there is a central limit theorem with a variance here that we have an explicit expression for, at least in terms of these variance components. Now, an important aspect of this is that I have added in the centered my random forest around its expectation, as opposed to some sort of targeted truth. We did that in this way because we wanted to be fairly agnostic about what this tree building process was. And there's no real way to get around an analysis of bias without going into the weeds of how you build trees. So Stefan Bager and Susan Apey, in a really nice piece of work in 2017, came up with a similar type of result in which they were able to replace this expectation with the expected value of y given the x star that you're interested in. But to do that, they had to make specific assumptions about how you build trees, and to some extent their statistical properties that don't quite align with standard practice. You can make some good arguments that maybe we should change standard practice. Some of them, it's a little less obvious. That's really common in trying to analyze trees because they're very, very hard to get to. So it's a really beautiful paper, and you can get to that. But you do need to do work on the specific sort of base learner that's going into your ensemble to get there. Okay, so I've got these variances. Let's look at what they are and how I might estimate them. And keep an eye on time. Oh, I am not going very fast. Okay. So to estimate these, what are these written as? Well, zeta 1 is the main thing that you look at, and it does seem to be the one that dominates. It's basically the variability. The easiest way to write it is it's the variance of what you get if you take the expectation of h over everything except x1, and then take the variance of that. And there's a simple way to estimate that. You fix your first input into your tree, you sample the rest of the subsample several times, build a tree on each, average those, then choose a new x1, y1, and repeat, and then you take a variance across those averages. Zeta k is just the variance between the trees, and we just take the variance between the trees. So you can do this by structuring subsamples. You don't need to recompute your trees. You basically get this variance at no additional cost. Now, that's a very naive and not particularly optimal way of estimating particularly zeta 1. And I'll come back later and discuss better ways of doing it, but it does in fact get fairly clearly at what these things are, and also why you might say, okay, I don't want this guy, zeta k, to be more than k times zeta 1, because this really is like an average over k things instead of a variance over 1. Or a variance over something that looks like an average of k. Now, if we do that and we calculate variances a couple of different ways, this is just a few points where we are looking at the probability of seeing an indigo bunting in Stewart Park in Ithaca, if I remember this correctly. And you get a set of confidence intervals. Now, this is based on tens of thousands of observations that expand with the probability in exactly the way you would expect a binomial to. There are a couple of different ways of estimating the variance agree with each other. That's nice. And these confidence intervals are somewhat wider than you might normally have expected from a really enormous data set. But that's part of the lesson, is that in fact there's more uncertainty than you might think. Okay, so I can produce confidence intervals. What else might I want to do? Well, I want to test feature significance. So I might say, oh, look, I wonder if current maximum temperature really affects the presence of these birds. And so I can say, well, are my trees really using it? And one way you could do this is to say, well, let me build a model that uses current temperature and one that doesn't, and I'll look at their difference, which I can write as a difference of the trees. Oh, that's what we use statistics. So here's a framework. I'll look at a number of predictions. They'll have a joint normal distribution asymptotically, or these differences will have a joint distribution asymptotically. I can form a chi-squared statistic and use that as a test. And that seemed really cool. When we tried it, it didn't actually work very well. That is, we gave the trees noise and they said, no, we're using this. And that turns out to actually be not terribly surprising, because the trees will actually detect the dimension of their covariate space. And so they have different expectations. And in fact, Lucas has a really neat paper that's gone up on arXiv where he says, actually, you can regularize random forests by giving them more noise columns. And it actually improves performance, which is kind of surprising. So our workaround for this was just say, well, look, let's permute that noise column. So rather than dropping it when we build this reduced forest, we'll just give the forest a nonsense version of the noise covariates. And we'll test the difference between trees with permuted and non-permuted noises. And you could develop a whole permutation distribution if you wanted, but using chi-squareds works pretty well. And basically we say, look, do true permutations make a difference? No, you really can't tell them, and it seems fine to use this test. So an example of this, does year make a difference? Well, if we test whether or not the year it was collected made a difference, we drop it, certainly seems like it's highly significant. But if we replace year just with a randomized version of it, it still looked highly significant. We can't tell the difference between two randomizations of that column. And so if we look at the observed value versus the randomized value, so trees using the observed value versus trees that get the randomized value, we actually have a strong test statistic, and we're prepared to say, not very surprisingly, that there's differences in abundances over these years. Turning this into a sort of more formal and interesting topic, Tim Coleman took a set of regions where I think this is till tree swallows like to stop. They're insectivores, and so we thought that the daily maximum temperature might make a difference. And so we ran this test, especially during the fall migration. There's this hypothesis that the birds are migrating later because the temperature stays warmer and the insects that they eat on remain around and basically still alive for them to use as a source of food. And effectively, we find that appears to be the case. When we look at partial effects at each of these locations, so just looking at what happens if you change daily maximum temperature at each of these locations over various days of the fall, so this is kind of an interaction, you see something where this is more positive early on and then switches to more negative, and that's in line with what we're expecting. Okay, so it's getting close, I think, to when Tal would like me to stop.
I think take your time. Thank you.
Okay. Well, you know, I know we might all be virtual, but we do have schedules, so I won't pray on you too long. A couple of things of sort of variations on this. One is on these variance estimates. These have the form of a conditional expectation, and in fact, estimating the variance of a conditional expectation is a difficult and not unstudied problem. And so ideas to do this for random forest and go back to 2009. Stefan Weger applied the infinitesimal jackknife, although just as a heuristic. Also then there's ours. And there are ideas from Sun and Wang and Lindsay and Goda about how to do this as a generic problem. What you get when you look at estimates for this are all things very similar in the formula that you arrive at, even when you get to them by very different means. They're all biased upwards because of a Monte Carlo expectation that I'll try and explore. But those biases scale with the number of trees. So you can build very large forests and get decent uncertainty quantification, but that really adds to the computational cost. And if you build forests according to the defaults in, say, the original random forest package, so 500 or 1,000 trees, you get a severe upward bias in your variance estimates. So a lot of these estimates I've done are built with order of 10,000 trees instead of 1,000. Just to let me show you that, I'm going to look at three potential candidate ways of calculating this variance. There's what I just showed you, which is to say I'm going to take a Monte Carlo sample over possible subsamples for this expectation of the value of H conditional on, I should say, Z1, as Z being Xi and Yi, so the first observation. This is joint work with Jungsu Zhou, and Jungsu said, well, look, rather than restructure everything, how about what you do is you say, for every observation that you have, take the average of the trees that use that observation that got to see that observation in the data set they were given, and then take the variance over those trees. So this is just being, he's called it balanced. This is just being a little more holistic in calculating this sort of internal method. And then the infinitesimal jackknife looks quite different. It says, let me look at the covariance between the trees and an indicator of whether or not the ith observation was given to that tree. We'll square those covariances, so this is covariance across trees, and sum up those squared covariances. Now, what do I get? Well, here is a little sample using simulation using these trees, 100, 1,000, or 10,000 trees. And I've got the log variance estimates are the bar graphs with the actual observed between tree variance given by the red line below here. So, sorry, between forest variance given by the red line. So we did a simulation to get the variance between forests. And what you can see is this is of the log scale. The bias here is orders of magnitude at 100 trees. At 1,000 trees, it's still one order of magnitude, and the stuff that Lucas and I did is not performing terribly well, and maybe not terribly surprising. And you know, you do need to get up to 10,000 trees where you're still noticeably biased, but it's getting better. Okay, so where does that bias come from? It comes from this Monte Carlo estimate of the expectation. And so if I take a variance of a noisy estimate, I get the variance of the estimate included is part as a bias on the variance of the non-noisy expectation that I'm interested in. And I think it's easiest to see this in the internal method, but in fact, you can write out that bias also for all of these other methods. Now, if you try and correct that, it actually turns out you tend to get pretty noticeably negative variance estimates. And the reason for that is the natural correction is to look at the variance between the trees. But that itself is biased upwards. It's biased upwards because when I subsample without replacement, my trees are negatively correlated. If observation 2 gets included in tree 3, it's unlikely to also be included in tree 4, or it has less likelihood of being included in tree 4 because I'm not allowing repeated sampling. If I replace subsampling without replacement to subsampling with replacement, I fix that issue. And my bias correction is unbiased. Phew. And in fact, you know, with 100 trees, our variance estimates are pretty noisy, but up to 500 or 1,000 trees, we end up with corrected variance estimates that are pretty much bang on the money and can work pretty well, basically with the defaults in random forests. So in fact, all of this works under the standard random forest R package, and you can implement all of this without actually having to write more code, except for the variance estimates. Now the problem is, okay, I no longer have variance. Sorry, I no longer have a U statistic. I'm sampling with replacement, not without. I'm still doing a subsample. And so this is what's called a V statistic. And, you know, naively, oh, hey, most of the texts say, look, V and U statistics are asymptotically equal. In fact, they're asymptotically equal really fast. We don't have to say anything more. Now, that turns out only to be true if your subsample size grows very slowly. But if I do a little bit of accounting, I can write any V statistic as a U statistic with a different kernel that accumulates basically which elements of the subsample are duplicated or triplicated, et cetera, in the sampling with replacement. And so there's a kernel that's associated with how many unique elements you have, and we have to sum that over with a partition of how can we partition them out into this U statistic kernel. But at that point, all of the rest of the crank falls out, and we have a standard corresponding central limit theorem, and basically the variance estimates that you would want work exactly the way that you would expect them to. That's just been updated on archive, and hopefully will be out soon. Couple of other things. The other way you might want to deal with creating an ensemble of trees is instead of sampling and building trees with an IID process, you might want to build them in sequence. And this is the idea behind boosting. That is, in a regression setting, what I will do is I will take my current predictions, look at their residuals, build a tree to predict those residuals, and then add that tree onto my current forest. And so I can keep on building up my forest in sequence. And the idea here is that in a random forest, if the trees keep on targeting one particular part of signal, they're a nonlinear projection. So they'll all go after a particular part of the signal. And you might have some signal elsewhere that you could pick up with a tree if that was all it had to do. And so you can reduce the bias somewhat, but this is harder to estimate. One of the ways you can do this is with just simply boost random forests. And so Indra spent some time looking at saying, well, I'll build one random forest, and then I'll build another random forest to predict the residuals from the first. This is a sum of two U statistics. Under some conditions, you can generalize it, generate a CLT, and do some variance estimates, and things work fairly nicely. I'm putting this up here because this improvement column is the percentage reduction in test set error relative to random forests for gradient boosting, a bias correction idea that Lucas and I had come up with, and then a couple of different variances of versions of random forests. And then we have also confidence interval length and coverage. And basically these positive numbers are positive reductions in percentage reductions in test set mean squared error. And you can see some of them are pretty damn huge. So 70% reduction in MSE is huge. It comes down to sort of 3 or 2% in noisy data. And you get better reduction in higher signal to noise ratios. But in fact, we don't have a real world data set where this fails to improve your performance. There is one data set. Actually, the forest fire data set, even a single random forest does worse than a constant, so I'm not really going to count that. Now, in simulation, you can certainly make this noisy enough that doing more modeling, adding the boosting step, does break this breakdown. And it becomes harder to make this work for classification for that reason. But in a huge number of real-world data sets, it just makes a big difference and seems to actually really fairly reliably improve what you get. So I've been completely surprised. We're not the first people to think this up. In fact, you can plausibly see it as a bias correction suggestion in Bryman's original paper. We're really surprised it just hasn't been sort of more generically used. We also looked at trying to do actual gradient boosting, and so build individual trees in sequence. And we did this by, rather than summing up a bunch of trees, keeping a running average. And if you do that, I'm not going to go into a whole lot of time because I think I really am pushing this out. If you do that under fairly restrictive conditions, you can get a central limit theorem. This turned out to be much harder than I thought. Poor Yichen, who is fantastic, now working at Google, had I thought was a project that would take him a couple of months, and it took years for it, not his fault. But you can get something out of it. One of the reasons I wanted to do that was that the boosting framework allows you to start interleaving different types of models. So you can start trying to produce a linear regression with a tree in a partially linear model, or something that looks like a varying coefficient model, or something that looks like an additive model. And there have been various people suggesting doing these types of producing these types of algorithms. And so if you can start doing that sort of structured algorithm and produce a central limit theorem for it, then with a bit of luck, I can say, well, you know, I've got some high dimensional Z, but I'm really interested in this linear trend, and I can still get inference about beta as well. And so we're partial of the way there. There's a lot to go. I'm going to not talk too much about this variant coefficient model for Beijing housing data because I think we're out of time, but I can do that later if you want. So further things you can do, you can translate this into stability of model interpretation. You can look at additive models. We spent some time taking complex models and trying to produce individual trees that would mimic them well as a way of producing explanations for decisions. I'm currently working on doing density estimation because you can use random forest to generate conditional random variables really nicely too. But the overall message I want you to take away with is, you know, in 2001, Leo Breiman wrote this essay in statistical science on the two cultures of statistical modeling, in which he really sort of contrasted classical regression or other statistical model methods with what he called algorithmic modeling. And there was a kind of never the twain shall meet feeling to that. But I think really you can bring those together. And in fact, there's an awful lot of exciting work to be done in doing that. But when you do so, the theoretical details make a difference. Getting your variance estimate right is actually challenging and important, and you have to do some good theory to make it work. And there's an awful lot to do, not just in random forest, but lots of other things like deep learning. And I am going to leave XKCD to sum up my views on the plausibility of that. So thank you all for staying with me. There are still people around and have time. I'm more than happy to answer questions.
Okay, let us thank Giles for his quite interesting talk. And if you have any questions, please just directly unmute yourself and ask. Thank you. Okay, hi Giles. So I have a question about your theoretical framework. So I think it's a brilliant idea to use the U statistic to analyze the theoretical properties of the random forests. And also it's my first time to attend a seminar like this, so I'm quite excited. So my question here is that, so you basically revised the random forest method a little bit such that it can adapt to the U statistic framework, right? So my question here is that in this case, I think the sampling strategy actually changes, right? So in this case, from the empirical point of view, so can this method have a better prediction performance than the original random forest method?
So the experience that we have is that you do want large subsample sizes. And the original central limit theorem we had actually had the subsample size grew like the square root of n, which wasn't ideal, and the new refinements that Lucas has put up get this up to being little o of n. You can often find that there is a small improvement our subsample size from being a full bootstrap sample a little bit, but it usually wants to be somewhere up near there. Sorry, I see a chat that might be suggesting that I'm still not understandable. No, we'll answer that later. And you know, the shift between V statistics and U statistics mostly seems to be a wash. So, you know, these are hyperparameters in some sense, so you can tune them a little bit. Again, so long as your subsample size is relatively large, it doesn't seem to be super sensitive to it.
Thank you so much. So any more questions? Oh, yeah.
So there's a question in the chat. So is there an implementation in our other software with variance estimates, confidence intervals, and hypothesis tests? Some. For the nice, relatively complete software implementation, the R package Ranger actually does do variance estimates. They're based on the infinitesimal jackknife. That's not very different to what we would regard as state of the art, although it doesn't have the bias correction that we like in it. And it's based on the Vega 2014 paper. There is also a package on GitHub called surfin as subsample random forest inference that my student Sarah Tan wrote. That's a little bit more basic. It doesn't have a whole lot of bells and whistles attached to it as yet, and we've been debating how much we should try to write our own versus actually, produce as opposed to piggyback off other people. In fact, the variance estimates are pretty straightforward to produce, and you can actually recalculate themselves in a few lines of code out of Ranger or out of Random Forest. Unfortunately, you can't do something generic because they don't come in the same format, but they're not very hard to do. Let me say, another question. With sequential boosting, does the order you apply each machine learning algorithm matter? Right. So little more detail on this sort of process, and in particular, what we did with additive models and boosting a long time ago was to say, well, we'll cycle through each covariate and build a tree on that covariate. And I mean, a univariate tree seems a little bit silly, but it does do some adaptive smoothness, so it's not completely ridiculous. But we'll build a tree on each covariate. And then what you do in boosting is you build a tree on the current residuals, but you shrink that tree, usually fairly severely, like by a factor of 10 or by a factor of 100. And so you're only adding a little bit in. And then you move on and you build one on the next covariate and do the same thing, and you cycle around. So hopefully the order in which you use, of course you could randomize that, the order in which you do that cycles out. In linear regression, the equivalent form that's being explored by Peter Bullman in particular has been to say, look, what I do is I cycle through the covariates, and actually I find the covariate that most improves my prediction, and I increment its coefficient a little bit. And so that would be a kind of framework from which you might do this additive model. And there's a package mboost that does that. It actually insists on I'm going to look at the best thing rather than I'm just going to cycle through everything in random order, but that's not also not terribly hard to do. And those, end up producing pretty decent models. You can look at it as a form of backfitting. So I think, this looks like it might work reasonably well.
Thank you so much. And any more questions? So Giles, I have the last question. So based on my understanding, I think some researchers also have shown some theoretical properties based on the original random forest method. So so based on your method, so do you have some comparison between the confidence interval based on two different theoretical frameworks?
So most of the theory that I'm aware of that's looked at sort of trying to get at the original method, because this has turned out to be a difficult thing to get a handle on, has come out of Gérard Biot's group in France, and they've largely looked at consistency. So the only major result that I'm aware of is consistent for exactly the original random forest is a consistency result when the underlying function is additive. But they don't do anything by the way of uncertainty quantification, or that's different to using the infinitesimal jackknife or anything like that. And I don't think they do a central limit theorem. I saw a paper came out on Archive just a couple of weeks ago that looked at rates of convergence, which they claim, if I recall, is there for the original random forest algorithm as well. But again, that's not a distributional result. That doesn't mean that it isn't really interesting work and super challenging to do. But, so there's not a lot on there's not a lot out there besides this stuff on uncertainty quantification that I'm aware of. I'm still, you can see ways in which you might think that you could get a CLT for the original random forest, but it's actually really challenging because of this non-disappearing overlap between bootstrap samples. So, you know, there's various methods. There's also a question of, you know, do we have to stick with the original random forest algorithm? Is that in fact better than something that we can analyze explicitly? Vega makes an interesting, Vega talks about using honest trees in which he takes the subsample he's going to use and then further divides it into a portion that he uses to choose the structure of the tree. And once that's set, he uses the other portion of it to decide on the values to give in the leaves, so the actual prediction to make. And there's actually some good reasons in edge effects to say that might actually be a good idea. On the other hand, you get extra bias because your trees can't be as deep. So some of that's not super clear. I don't think that just because Leo Ryman wrote it down, we are necessarily stuck with the way he did things. Interestingly, if you look at Ranger or the random forest package in R, the subsampling with or without replacement as opposed to full bootstraps are all options you can choose right now. They've all been ended up adding as just extra hyperparameters to random forests.
Thank you so much.
For a question about implementation, if someone is there, I should also point to the GRF package for generalized random forest that Stefan Weger and Susan Athey put out. That does a whole lot of interesting stuff there, and certainly includes the infinitesimal jackknife and other variance estimates. All right, well, thank you all for being around. This was an interesting learning experience for me. If I have a set of bibliography here if anybody wants the slides from me. And again, thank you all for being here.
Thank you so much, and thank you all for joining this Zoom seminar, even though today the internet is not ideal. And next week, we are going to have an actuarial seminar, and after we will go back to statistics seminar by Professor Hanling Shang. And the notification has been sent, and please take care and stay well and safe, and see you next time. Thank you, Giles.
Thank you. Cheerio.